start talking today. Yell if I need to move my head. Maybe I'll just go ahead and move my head. I think that's going to get in the way of, yeah, I'll put myself there for today. I think that should allow us to see most stuff. Maybe I'll make my head smaller as well. There we go. Okay, microcephalus for the HADC meeting. Okay, welcome everyone. I'm just going to drop a link to the schedule in case people are interested. I had had this idea based on, it's been a while since we've talked about effect size and statistical power. And so today I'm just going to introduce the idea, and I've got a statistical power cheat sheet that I made some time ago. I'll go through that with you, and there'll be some coding and just a small introduction. So it's the idea of the tools that statisticians and scientists use to determine how much data you need to collect. This is a lot of statisticians think that this is the most important statistical topic ever. And Sophie, I saw you join. Do I spy you in the chat now? Yes. I thought next week someone has asked me to calculate a specific effect size, and it's actually quite hard to do that from the literature when you're starting out. And so I thought we would go through an example, a real example of doing that next week. If I can't think of something else, I have a few ideas to follow up on using AI for statistics. So I thought we would do that the week after that, and not sure about the last few weeks of the year, and then a break before January. So that's what's in the cards. If you want to follow along in the slides, you can click the Canva link as long as Cloudflare is playing along. So I'm going to go through this right now. So yeah, this idea, I've talked about statistical effect size and calculating your sample size, and these jargon terms, effect size and power. Talked about them quite a lot in this group meeting over the years, but it's been a while since, maybe at least well, it's been more than a year, I know, since we've talked about it, I believe. So I thought it was time to revisit it. We want to think about something that we might call effect size thinking. And this is a way to think about your experiment. A lot of scientists, and this is very natural, a lot of scientists, you're thinking about your experiment, you're thinking about what data you want to collect, you're thinking about your hypothesis, and then you collect all your data, and then you get to the end of your experiment, and then you're like, oh, how should I analyze this? Maybe I should speak to someone and get some advice on that. Well, some people would say that that's the opposite way of thinking about data collection, to a way of thinking called effect size thinking. And this way of thinking asks the question, before you collect any data, that you should think about exactly how much you need to collect. And you need to think through a few things and have some knowledge. And often this is, there's a learning curve to this. So to be able to answer the question of how much data you need to collect, you need to know something about how big the difference is that you predict. And for example, maybe that you're working on something like like a growth rate in some sort of livestock, and you have two different feeds, and a control, and maybe an organic one, and maybe something with the different ratio of nutrients or something. And you want to see how that affects the growth curve. And you predict, well, this new formulation that I'm testing is going to be bigger than the control, the gold standard. Oh, that's great, Sarah. They're welcome in, and I hope some of them join. Well, the idea with the effect size thinking and to calculate your sample size is that we need to be a little more specific than just saying it's going to be bigger. We need to think about how much bigger it is. So I'm going to just introduce the real basics of the idea of how to be more specific today, and then I'll end up with a cheat sheet on how to do your own sample size calculations if you want to start thinking about this. I look back when I was trying to see what materials I had to prepare for this, and I thought I'd show this on a slide that in 2019, at the very first meeting for the ancestor of this group, which we call HADC now, the topic was effect size thinking and power analysis. And this was the first slide that I showed. And back then we were still even thinking about the name. We hadn't come up with Herrig yet. It was hair up. I think it was the U and the P on the end of group, but I thought I'd just show that. So this really revisits the same topic as that. I've also borrowed this slide from it with a little bit of modification. Is that here's a way to start off with effect size thinking. Let's say that you're doing an experiment and you want to analyze it and you want to get a statistical result and you want to reject the null hypothesis or accept your alternative hypothesis. Well, a way of thinking about this is there are four possibilities for the outcome of your experiment. In the real world, if you actually knew the truth, as scientists, if we knew the truth already, we wouldn't have any reason to do an experiment. So in the real world, these two columns represent whether the null's true. You hypothesize the null's false. That's what scientists do, and they design experiments to falsify the null. But in the real world, in this column, you're wrong. The null is true. And in this column, you're correct and the null is false. So your hypothesis is correct. Down here on the two rows is your conclusion based on your data analysis. And here you conclude that the null is true. And here in the second row, you conclude that the null is false. Well, this leads to four different possible combinations of outcomes. Up here in this upper left corner, where in the real world the null is true and you conclude the null is true, you've made a correct decision. Your conclusion matches the reality of the real world. You're wrong. Nobody wants to be in this square, but you are correct that you were wrong. Down here in this square, the lower right, here in the real world, your hypothesis is correct, the null is false, and you conclude the null is false. And so this is the box that everybody does want to be in. This is the preferred box. It's a correct decision. But for today, we're going to talk about these error boxes. And the first one we'll mention is when the null is true, but you reject the null. This is a false positive. Now, the type 1 error, there's a probability associated with making this kind of error where you get a false positive. And you don't want to make a false positive because that leads to paper retractions and people can't replicate your experiment and it's a weird result. So you never want to be in this box. Although, of all the mistakes you can make, getting some positive signal, some people might say, I'll take it. But it is still something to avoid. Well, what controls the probability of the alpha in the type 2 error? Well, this alpha is the value of the probability of making this error. And that's the threshold that you compare your p-value to. I'll talk a little more about that in just a moment. But up here is possibly the worst error you can make in all of science. This is a false negative. This is where your hypothesis is actually correct, but you fail to reject the null. So this is called a beta or a type 2 error, and the value of beta determines the probability? Well, let's talk about the alpha first. This is the one that everybody's familiar with. This is the one you already are probably comfortable with the idea of the alpha. This is the type 1 error rate. It's completely controlled by the researcher. And this is the probability cutoff that you assign to your own experiment for your significance test. And the probability we set this to, remember, this is the probability of having a false positive, is 5%, 0.05. That's where the 0.05 threshold comes from. It's associated with this error, with alpha. In theory, any probability value can be chosen by the researcher. You're in control of this. It's a philosophical framework that the researcher, the analyst who's doing the data adheres to. And then there are some fields like human medical biology and some environmental and geographical things, financial market statistics as well, where there is a trend to deviate from this 5%, usually by making it lower. But for almost everybody else, certainly for the kind of natural and applied scientists that most of us are at Harper, the traditional default value is 0.05. And even though in principle you could change it, no reviewer or other scientist would accept your moving it, especially if you made it higher. You could always make it lower, though, make it more strict. The thing we're talking about today is this type 2 error, the beta. Now, this is also controlled by the researcher. Remember, this is the probability of having that false negative. So you're correct, but you failed to reject the null. This is a disaster because you wasted all your time collecting your data. You were right, but you don't have any evidence to show for it. Now, I said that the traditional value for the alpha, if I just go back a second, is 0.05, and we're all comfortable with that. Does anybody know what the traditional value for beta would be? If you had a probability between 0 and 1 of being correct, but making the error of not having not not being able to produce evidence for it, what's the highest probability of having that kind of error you'd be willing to do an experiment with? Would anybody just put that in the chat? Maybe everybody could just put, what's the highest probability you would want to put in the chat? I mean, you might be tempted to put 0, but that's not realistic. See, Sarah put 0.2. Try 0.2. Yeah, okay. A little bit higher. Anybody else care to venture a probability? I can see we have some experienced people in the chat because if we think about this thing called power, this is the probability that it's the inverse of the probability of being wrong for a type 2 error. It's the probability of being right, and it's 1 minus beta. And the preferred threshold that's traditional is 80% for power, which is indeed 20% for beta. So what we usually think about is this power. We want to achieve 80% of being able to be correct and have evidence for it if we are correct. Way to think about this is that if we get much lower than that and you have a binary outcome, if you go much lower than that, you're approaching 50-50. It's like flipping a coin as to whether you've wasted all your time collecting your data. There are lots of reasons to think about power and take this seriously when you're designing your experiment. I mean, one is the one I've hinted at, is just the efficiency of collecting data. Doing your research is expensive in terms of actual money that it takes, and time, in terms of the resources that you consume, in terms of the time that you and other people consume. There's an ethical angle often. If you're dealing with animals, for example, by by evaluating exactly how many samples you need, you can minimize the number of subjects that you use without having too many. And so that maximizes the value of their sacrifice. Likewise, if you do too few and you make a mistake because you have that type 2 error, that's disaster because you've wasted all of those animals. So it's very unethical. Some people consider to not consider power all the time very seriously. Practicality as well. Um, More and more over the years, there was a spike. I think over the past 20 years or so, I've observed where lots of journals and some grant funding agencies um, will invite formal power analysis as part of an application. It never will weaken an application. Some mandate that, especially some journals. They tend to be specialist journals these days, but the awareness of the practicality of it is out there. And then just it's best practice. If you're not going to take this seriously, maybe you should just go home. You don't want to waste your time and that of others. Now, there are several types. We're going to talk about several types of power analysis today. I'm just going to demonstrate a couple of the real simple ones these days. But the thing I want to say up front is that every kind of statistical test tends to have its own measure of effect size. So when I say effect size, there are several types. There is generally a different method to calculate the effect size for every different statistical test. And some of them are easy to calculate. I'm going to show you some of the easiest ones for today. But maybe if people are interested, we can talk about some of the more complicated effect sizes later, especially ones that are part of common experiments like mixed effects models and repeated measures models. Those are a bit more complicated, and we might even mention them next week. Okay, so one is, and I also should say this, that a lot of the ways of calculating effect size derive from just, in general, two broad categories. One category is an association statistic, and one of the simplest association statistics is correlation. And in fact, if we look at the correlation test, the effect size is measured by the correlation coefficient, little r. And I just have an example graph here of a couple of different effect sizes here for a correlation of 0.476, about 0.5. You can see it's not a real strong correlation. There's a bit of scatter. Um, this 0.476 is the effect size of this test. Likewise, 0.528. This looks similar to this one. And a very high correlation coefficient is 0.986. And you can see it's almost a straight line. Now, I'm not going to go through this today, but in the history of talking about effect sizes, a person I'll mention, a researcher that I'll mention, an applied statistician who's very celebrated, is someone called Jacob Cohen. And I'm not going to formally go through it for this slides, but in the code session, I'll tip my hat to what Jacob Cohen called rules of thumb. So the rules of thumb are suggested effect sizes for a small effect size, a medium effect size, and a high effect size. And the reason that Jacob Cohen offered these rules of thumb is that oftentimes when we want to get specific about our hypothesis, we don't have a quantitative estimate of it. Maybe we would have to do a pilot experiment to do that if we have a really novel experiment. But oftentimes we're constrained. We can't do a pilot. Or maybe we want to extract something from the literature, from the available evidence, but maybe we can't find anything that's quite right. And so that's why Jacob Cohen formulated these guidelines. Now, the guidelines for correlation coefficient are that around 0.5 is a medium effect size for the correlation coefficient. And he has different ways of calculating and different thresholds for different tests. But I just thought I'd mention that. So we may bring it up in the code section later. So correlation and association is one of the big categories of effect sizes. The other one is the other type of effect size is a type of a difference where we're comparing two things. This could be a control and a treatment. It could be two samples from different populations, whatever they are. It could be observational or it could be experimental. Now, the difference and different versions of the difference statistic are derived from a quantity called Cohen's d. And again, Jacob Cohen is sort of generally recognized as the statistician that formalized these ideas and described mathematically Cohen's d and generalized it to many other problems. So, like for a t-test, Cohen's d is the specific comparison. The way you calculate that, this is a good way to think about the intricacies of the effect size, is you can measure the difference between the means. Here, the dashed lines in this box plot are the means of these two samples. And the difference along the y-axis between those dashed lines, well, that's the numerator for calculating Cohen's d. It's the difference between the first mean and the second mean. And actually, it's the absolute value. We don't care whether it's positive or negative. It's just the magnitude of difference. And then we also need to consider the variation around the means. You can imagine if the difference is small and the variation is really big, that there's probably not a big effect size here. Likewise, if the difference is big and the variation is small, probably is a big effect size. So the denominator for Cohen's d is the pooled standard deviation. So it's a measure of the variance standard deviation. It's pooled because for a two-sample t-test, we weight the total standard deviation based on both samples. That's just a little detail that I put in. I probably could have left that off. I did mention a couple of papers. These are papers that I mentioned back 6 years ago in that first meeting. And these are papers that I think a lot of applied scientists should be aware of and possibly even take it seriously enough to actually read them and discuss them with each other. For example, if you were, it's not a tradition in Britain, but in other parts of the world, it's a tradition to give a reading list of the classic literature to PhD students. And many of them will be in the subject that you're studying for the program, not necessarily your specific PhD topic, but for the program you're studying, the classic papers in environmental impacts, in agriculture science, in spatial data and farm management, depending on what you're studying, what program you're on. But there usually are some general papers about the practice of science. And these are two papers that I think should be on lists like that for most applied scientists. One of them is a paper in a psychology journal that Jacob Cohen published. I think this is quite old. It's one of the real citation classics of all time for data analysis. And it's not by, I mean, I called Jacob Cohen a statistician, but he's an applied statistician and his background was in psychology. What this paper is about was a phenomenon that he discovered, that a lot of the published papers in the field of psychology back then, those many decades ago, were biased. And they were biased because many of them were very low statistical power. And he made a very strong argument for that, and he wanted to correct best practice. So this is the first classic paper. It's got thousands and thousands of citations. And then a friend of mine, Shinichi Nakagawa, wrote on a more recent paper. It's also a citation classic that I think most applied scientists should read. And it talks about low statistical power and publication bias, this time in the natural sciences. Okay. And if you like books, if you are a mathy person, Jacob Cohen's book is still I have two copies of it over the years. I use it as a reference, less and less over the years, but once or twice a year I crack it open. It's published a long time ago, and it hasn't changed. The math is still the same as it was, but he gives lots of examples of how to calculate everything. No software whatsoever, just lots of experimental designs and how to calculate the effect size and power for every single one of them. Probably for most people, this is a better book, the Quinn and Cuff book. It is also quite old, but I don't know of a better experimental design book. Again, no software. It's not applied. It's just talking about the ideas. Both of these are real good if you like books, but these papers are citation classics, and they'll really give you an idea for what the ideas are. All right, that's all the slides. For today, I did resurrect something that, again, if we go back to the page, there's a link to the GitHub. And if you like this kind of thing, I've included that original talk that I gave the 6 years ago just to document it for posterity, if anybody's interested. I downloaded this PDF of the slides that I just showed you because Cloudflare was acting up earlier. But what I want to show you now is these two documents, explain what they are. I don't suggest anybody download this document, but I'm just going to show it to you real briefly. At least not download it today, right now. So I'm just going to open this real quick. And what this is, I've updated this. This is a tutorial that I created quite a while ago, a lot longer than 6 years ago. And what it does is it walks through different methods for common effect sizes using R. And it has some citations here. Just going to make this a bit bigger for people. Mention some of the classic citations, but I also mentioned some of the classic software. So R will take you pretty far, and I'm going to show you code and have the script in R that you can play with today. But a very powerful graphical user interface program is G-Power, G-Star Power. It's free. It's, I'm not sure if it's open source, but there are some academic papers about it, and it was created by some people just to help other people calculate power. There are other alternatives for calculating power, other software as well. I find R, believe it or not, to be easier than some of the other graphical user interface software. And if you try G-Power, you'll see why. But what this entire document is let's see if I was smart enough to put in. I don't think I have this set up to be an outline, but it's essentially a cheat sheet and tutorial that demonstrates for lots of different simple statistical tests, like the t-test, correlation test, chi-square, one-way ANOVA, linear models with multiple variables, comparing proportions. And it's just a tutorial to go through that demonstrates code to calculate all those simple tests. So this would be something for you to go through once we go through the code today, and you just listen this time. If you download the R file, again, it's just this file. You'll see something like this, and I'll make it big enough for everyone to see. I think I'll just get rid of stuff in the global environment. Make this wide so that people can read. I think that's big enough to see. Set this up in the way I like to set things up, with a header, a lot of contents. We'll see how much we can get through in the next 30 minutes. I think we'll be able to get through most of this in the next 30 minutes. Now, there turns out these days there are quite a lot of power um, analysis and effect size packages in R. My very favorite one is PWR. It's quite old. It explicitly implements Jacob Cohen's formula for all of the effect size calculations. And it's quite easy to use once you get the hang of it. So the point of this script is to give you a scenic overview of all the different kinds of tests you can do, at least some of them that you can do with the Power Package. It's one of the easiest ones to use, but you do have to get the hang of it and understand it. So if you install that, I'm just going to get it fresh. I'm going to load it up. You might have to install it if you haven't installed it before with install.packages, but I'm going to load it up. 3, 2, 1. Already got it installed. And one of the things I really like about this is it's got a series of functions. The one that I'm highlighting now, es.h, is to calculate an effect size called the H that has to do with comparing proportions. And so effect size.h, effect size dot whatever the name of your test is, you can generally bring it up. And you generally want to look at the help page to understand how to use the packages. I've got to remember the hotkeys to to create this. It's real convenient to look at the usage for functions that you're not an expert at using. So for example, for this one, I'm only going to do it for this function, so you can look through some of the others on your own if you want to actually go through the tutorial and use them. But this one's quite easy to use. To calculate the effect size for comparing two proportions, you need to provide two quantities, proportion 1, P1 and P2, which is the first proportion and the second proportion that you want to compare. So there are little hints like that for all of the help pages for all of these functions. So if we were to calculate the effect size for your proportion, and we wanted to compare the proportions for comparing 0.5 and 0.25, we could just run this 3, 2, 1, and we'd see that the effect size for comparing those two proportions is around 50%. And we could take that 50%, remember this is our effect size, and use the power function. So PWR dot whatever your test is, here it's a proportion test, we can insert the value that we just calculated, which is my proportion. Now, a thing I didn't bother saying in the talk, if I just highlight line 29, is that when we're calculating power, there are usually 4 things that we need to know. And if we know 3 of those things, we can always calculate the 4th one. So the 4 things we need to know are the effect size. Here, n is the sample size, and it's set to null because that's what we want to calculate. The significance level, by default, we would always set that to 0.05 unless you had a really good reason not to. And the desired value of power is 1 minus the beta, and the maximum beta by convention is 0.2. Therefore, the minimum power we want is 0.8. So that's a good one to start with. Sometimes there are reasons to accept a slightly lower power. Let me just say verbally what one of those might be. Maybe you have an experimental design and an experimental, let's say it's an animal experiment, and you have a practical limitation on the number of animals you can get. What you would use power analysis for in that case is to possibly calculate the power given your sample size. But in most cases, We want to calculate the sample size to achieve the minimum power that we can accept. All right, so we're just going to take our example here with a proportion test and calculate the power. We're going to get a little bit of output, so I'm going to make this a little bit bigger, and I'll talk you through the output. 3, 2, 1. There we go. Let's just look at all of it. So I've just submitted this line. This is a proportion power calculation for the binomial distribution. And we've got our effect size printed to us. We already knew that because we calculated it. Our significance level, our power, the type of test we're doing. We've got the number of subjects we need. So this means that we would need to perform an experiment with 29 samples. We'd always round up to if we wanted to achieve 80% power. Likewise, I guess I'll just leave this big enough so that we can read it and go through the code in this small window. I think that'll be okay for everybody. Here's an example where, maybe we only have 25 subjects available to us, like I was describing. Let's see what the power is. 3, 2, 1. So that whittles down our power. This is close enough to 80% that most scientists I've ever worked with would happily accept slightly lower power if their max sample size was reached, as opposed to redesigning their experiment or not doing it at all. Got some examples for comparing two proportions. Some more examples. It's a slightly different test, and there are some more variations in the power.2p test. So the idea for this test that we just did was we have some fixed probability that we're comparing one sample of probability to, but the 2p test is a little bit different. Here we've got two samples, each with their own independent probability. It's a subtle difference, but it's a little bit of a difference. Magda.
Thank you, Ed. Just a quick one. For the ESH function, you need these two proportions, P1 and P2. What are these?
Oh,
thank you.
yeah.
Sorry, if you introduced this earlier, but I just joined you late, so I might have missed it. Sorry for that.
No problem. Very conveniently, the help page is still up and the definitions of those are still there. And those are literally just the proportions you're comparing for a proportion test. And was explaining that the es.h, it actually works for both variants of the proportion test, the 1 proportion and 2 proportion, where you have, with the 1 proportion test, you have some fixed proportion, like flipping a coin would be 0.5 for a fair coin. And you come up with, let's say you come up with 35% heads. That would be an example of a kind of test, but it's just the proportions that you're testing in there. Every one of these functions for effect size has different things, and I just made the point that it's very important to figure out what those arguments are from the help page. All right, so I'm just going to go through these quite quickly because they're similar to the ones we've just done. This one compares two proportions that are actually quite close together, and it does a two-sided test. What is a two-sided test? That means that these proportions could be higher or lower in their absolute value of difference. And the effect that has that I wanted to demonstrate is that here the effect size is quite small for 0.5 and 0.4. That's not surprising for these two proportions. But because the effect size is small, you need a quite large sample size to be able to actually provide evidence with 80% likelihood, if there is this small difference that's real, that it actually exists. Now, if we look at the two-sided versus the one-sided, two-sided tests, if you haven't encountered this idea of two-sided versus one-sided tests before, that's okay. I'm not going to spend a lot of time talking about it because it's a bit of a technical detail, but there are two ways to be correct with two-sided tests. You could be higher or lower. And if I just run the one-sided test that's greater, 3, 2, 1, and we compare the sample size for the two-sided test versus the one-sided test because there's only a one way to do this test. The criteria are tighter, and it's therefore easier to demonstrate it for the exact same sample size. It's just a little technical point if you've encountered that before. If not, let's just carry on. I think I'm going to bring this out a little bit so we can see this whole thing. And I've just got some variants of how to use the power.t-test, p-test function here. Here I've shown a way of just testing the effect size by explicitly calculating the H with the es.h function. And we can do a little experiment. Here we're calculating the sample size. Let's just do that, 3, 2, 1. And well, the way that statisticians use these tools is we don't just run these once because there are some uncertainties. We're probably just estimating what these differences are. You know, what if the difference is a little bit bigger? Let's run that, 3, 2, 1. Oh, wow, that had a big difference. So we needed 69 subjects if that second proportion was 0.65. We needed 41 subjects if it's 0.6. And the reason of showing that is that these assumptions that go into calculating power and effect size are all important. And those rules of thumb I mentioned that Jacob Cohen gave the world, he did this to be very useful, to be a problem solver, because it is a problem if you're a researcher. I'm looking at some of you in the chat. Some of you have to do this now, and some of you will have to do it in the future. Making arbitrary guesses is bad news because it can really waste your time and those resources, your valuable time and valuable resources. So these assumptions about the effect size are all important. We must take them very important. And it's because they can have a big effect. That's amazing. 50% bigger experiment, more than 50%. All right, let's go to a simple one. It's the Cohen's d for difference. This is the classic t-test. It says that I have, this works for both one sample and two sample tests. One sample t-test would be if you have a known mean, like a gold standard of a mean, and you're just performing an experiment with one sample to compare it to. It's a bit unusual these days to do that, but I give the formula for Cohen's d. There is a, there might be an es.d, but I'm not using it here. I'm just saying, what if it's a small effect size? Cohen's rules of thumb for Cohen's d are that 0.2 is a small effect size. And here we know the sample size. We know it's a one sample test. It's a two-sided test. Two-sided should be the default, by the way, for almost all tests. Let's just run this. 3, 2, 1. And I have it in the comment that it's 0.33% power, which is too low. We would never do this experiment. It'd be a waste of time. So that's a small effect size. That is quite small. The difference is either small or the variance is very big. So, you know, again, the assumption is all important. Here's an example where we're calculating what effect size you would need for a very small effect size for a one sample t-test. Brace yourself for this. Wow, need almost 200 subjects. It's a one sample t-test, which is a pretty conservative and kind of a niche test, but just for a way of thinking about this, I wanted to go through this. There's a paired t-test. Now, paired t-tests are ones where maybe you're measuring an animal or a plant before and after some kind of treatment. They tend to be very, very powerful, these tests, because you're controlling for differences between individuals. I'm not going to go into why that makes the test more powerful in this code demonstration, but It's something that we need to keep in mind. These are very powerful kinds of experimental designs. Let's look at what a medium size effect size is for a sample size of 40 for a paired t-test. 3, 2, 1. And the power is very high. Look at that. Um, it's over 80, 87%. Let's just change that to to 0.2. Compare that to the one sample t-test. And with 40 subjects, well, it takes the power straight down, so it has a huge effect. Okay, the last little thing I have here is a way of calculating Cohen's d. Remember I said it was the difference in the mean, absolute value, and the paired or pooled standard deviation. So you could just calculate it on the fly if you have estimates of those, like I have here. Here the sample size is 30, and we're going to calculate what the power is, 3, 2, 1. And that results in a pretty beefy effect size. So close to a large effect size under Cohen's definitions. And the power is close to 80%, which is acceptable to most people. So that's pretty interesting. Got correlation. Correlation is the power.r test. And we have two-sided and one-sided, which could be greater or smaller. Here the correlation coefficient is, we'll just keep that at 0.3. With the first one, we're looking at a two-sided test with sample size of 50, 3, 2, 1. And our power is 57%. And let's see what happens for the exact same test for a one-sided test, 3, 2, 1. I guess for the two-sided test for a correlation coefficient is that we consider it, our hypothesis is that it's positive explicitly as opposed to the same magnitude of negative, which does make sense for a lot of predictions, but it increases our power is the point. And finally, I think we can just look at this one that shows the effect that a two-sided test has when we vary the correlation coefficient from 0.3 to 0.5. So let's look at the sample size for the lower one first, 3, 2, 1. So to detect a low correlation coefficient of 0.3 at 80% power, you need 85 observations. At 0.5, 3, 2, 1, only 29. And for 0.1, you'll need a much bigger sample size, 782. There's 10 minutes left. I think we have time to go through the last couple of examples. I'm going to skip chi-square, and I want to go to the general linear model, because this is one that I just want to show people what it looks like. It's a bit trickier to calculate, but it's very common, and people will want to be using this. To calculate the general linear model with any number of different terms in the statistical model. So this would be like a multivariate linear model. What most of Jacob Cohen's book that I showed you is about is calculating variance of linear models. And his statistic to do that is the F2. And I'm not going to go into it. I just want to show the function, because it's a bit of an involved topic to be able to estimate the F2. There are methods for mixed effects models, and there are methods for non-mixed effects models. Now, the effect sizes for F2 tend to be more modest, according to Jacob Cohen's rules of thumb. So the this is the U value is an aspect of the sample size where you have a certain number of treatment classes. In this case, there are three, but it's the degrees of freedom, actually. And then this is the total number of subjects across all treatments, the degrees of freedom that you have left. So this accounts for different experimental designs by using the degrees of freedom for your sample. So a downside of this, or it's not a downside, but it is a challenge for this, is that you do need to know something about statistics to be able to derive these. Most people who haven't had a few statistics classes at least would need to grapple with this. The F2 is the effect size. 0.15 is a pretty big effect size for this, or maybe it's a medium one, I believe, than the significance level. So what we'll do here is calculate the power for that test. I'm just going to calculate it real quick. 3, 2, 1. So the power is very, very high for an experiment of this size and that effect size. So this would be over 100 subjects for this. I think it would be about 102 subjects, probably. For the next one, what we're doing is just bringing the effect size down and looking at the effect that has on the total sample size that's required. 3, 2, 1. So we here are setting the power at 0.8, and it says that we would require a degrees of freedom of 57. So this takes a little while to unpack. This is one that usually statistical consultation is a good idea if you have this kind of model to do. The last one I'm going to demonstrate is the way of thinking. There's a bit of code in this, but it's a bit fun, and then it results in a kind of pretty graph. But it's not the code that I want to show you, and it's not really the pretty graph. It's more the way of thinking when you're designing an experiment that has to do with the assumptions you make. I'm going to talk through this code quickly, and you can. This is something that I would tend to do for every formal power analysis consultation that I do. I tend not to do it with PhD students, but for other kinds of people, I would tend to do this one exclusively. And the reason is, with a PhD student, it's your responsibility to mitigate all of the guesses that you make about that effect size. It's your responsibility to do it. For people in business, for farmers, for people at companies, they don't ever assume that responsibility. Instead, they want to weigh on the balance of, well, if I have to pay for this much of a sample size versus I make the assumption that my effect size is this big versus this big versus maybe I can accept a lower power. So what we do is we make curves, and you allow this way of thinking of, if I make this assumption, I can see on the graph, this is what happens. This is a standard kind of graph to do for, you know, especially applied power analysis, especially for statistical consultants. So I thought I'd just show this. First thing we're going to do is make a sequence of numbers, 3, 2, 1, which represent, if I just show what they represent a range of different effect sizes for a correlation test. Then I'm just going to calculate the length of that vector, which I think is something like 51, 41. Then I'm going to create a range of power values ranging from 0.4 power up to 0.9 power, and I'm going to increment that by 0.1, 3, 2, 1. So these are different power values that we might want to achieve in an experiment, and just calculate the length of that. Then I'm going to create an array, and I'm going to create an array that is of the dimensions of my correlation coefficient times the different dimensions of power. And that's going to be the dimensions of my array. So I'm just going to create that, 3, 2, 1. Just see that I've created just an empty array with all of those numbers. I think the reason I call this Felix, there's no real reason. I think I was folding into the script. Felix is a pretty stupid name to name a variable. I think I was just making the point here at some time in the past that you can name variables anything. They don't have to make sense, but it's better if they do make sense. So this is kind of a stupid name, but let's go with it for now. I just want to demonstrate that if we calculate using the power R test, that we can put the results into a variable. We look inside that variable, we just get the results of that test, like we've already looked at a number of times. And that if we look and see what class that variable is, it's a power.h test. So it's a kind of data object that R just defines with a name. We don't need to worry about what the name means. But inside this data structure are some names themselves. So they're names that hold the sample size, the correlation coefficient, the significance level and power, the alternative, and the method. And if, for example, we want to get the sample size out, we can use the cache sign in notation 321 to get the estimated sample size. Well, that's what I'm going to exploit in this set of for loops. I'm going to run the results of this t-test, and then each time I run it, I'm going to just grab out the sample size. I'm going to put it in my array at the locations I and j. So I'm going to fill that array with all of the required sample sizes to achieve a certain thing. I'm just going to run this paired for loops. They're called nested for loops. 3, 2, 1. Just takes a second, nothing to see. If we just look at the first few rows of my calculations, we see for different power levels and different correlation coefficients in the rows, you see the required sample size to achieve that given power, that combination. Okay, all of this has just been leading up to the last thing here. We're going to set up a graph to see what our assumptions mean. And I'm just going to scrunch the code. You can look back at this code yourself and see the graph pop up over here on the lower right. 3, 2, 1. I'm going to create a blank plot. And then I'm going to add the curves in another for loop. Show this a little bit. That go through the code that I wrote, or the array and the calculations that I made there. 3, 2, 1. Those are the lines. And add on a grid and some legends and a title. Now, because I've made my screen big so you can see it, it doesn't look very good. Here's what we end up with. I'm just going to redraw that so that it doesn't look so stupid. There we go. What this shows is that for different effect sizes and for different power that we can achieve, let's say you were designing an experiment and you think your correlation coefficient is between 0.2 and 0.4, but you're not so sure. And let's say that over here is the sample size. It goes quite large, 1,000 samples down to each of these lines is 50, each of the horizontal lines. But this might allow, if you think your effect size is between 0.2 and 0.4, maybe you would just average it and look at 0.3 for different powers. Well, you need, for achieving power of 0.8, the blue line, You would need well over 100 subjects to achieve that. But what this allows you to do is to look, well, what if I could accept a slightly lower power? What effect would that have on my sample size? And you can see how that affects the curves at different correlation coefficients. It doesn't really matter if you have a correlation coefficient of 0.5, but if you start to have a lower correlation coefficient, it starts to have a really beefy impact on your sample size. Now, if you can do this for any experiment you ever do, this is a very powerful way of thinking. That's all I have to say about that. Are there any very quick questions? Because we're just out of time as I am going to turn off the recording.